Okay, so now we're going to take a look in this section at some of the characteristics of one of the states of matter that we introduced back at the beginning of the semester, which is our gases. And as a quick reminder, remember we talked about the three different physical states. We talked about solids, talked about liquids, and then we also talked about gases. And we looked at some of the differences between these earlier on, and we'll take a look at some of the specific properties of gases here that are different from the solids and the liquid. So just a quick sort of orientation in terms of the elements on the periodic table that actually do exist as gases. There are very few of them that exist normally in the gas state. So from the periodic table, we did see several of these elements before. Um, so few elements exist as gases, but those that do include things like hydrogen. So hydrogen exists as a diatomic. So we have H2, we have N2, we have oxygen, we have fluorine, we have chlorine, for instance. And then we also have the noble gases. Remember, that's the group 8 elements. Helium, neon, argon, etc. Okay, so the noble gases, right? These exist as individual atoms, whereas obviously the other ones, these exist as diatomic molecules, but they're all gases. And the other elements can exist as gases if the conditions are right, but these are gases under normal conditions. So in terms of how gases differ from the solid and the liquid state, or the liquid phase and the solid phase, there's some pretty big differences. So for example, a gas assumes both the shape and the volume of the container, right? So the shape and volume of a gas is dependent on the container itself. Gases tend to be compressible, which means that there is lots of space between the gas particles, whatever those particles are, which means you can actually force them closer and closer and closer together so that you can compress them, in other words. What we also see is that the densities of gases are much, much, much smaller than those of either the liquids or the solids, and it can vary tremendously depending on the temperature and pressure under which that gas is being subjected to. So typically, the density of gases, or typical units that we use for the density here, would be grams per liter, whereas for the solids and liquids, the density, the units that we typically see are grams per cubic centimeter or grams per mil, right? So because the volumes that gases tend to occupy tend to be fairly large, we do have liters as our volume unit rather than milliliters for the solids and liquids. And then when we have different gases and we mix them together, they form homogeneous mixtures, which again that's another term for a solution. And they form these solutions with one another in any proportion where we happen to mix our gases. Okay, so for example, if you think about the air around us, okay, that is a solution. We don't normally think of solutions as gases, but solutions can actually be in all three physical states. And the air around us is a solution. It's a mixture. It's a homogeneous mixture of lots of different gases, the main component being nitrogen. And then we also have oxygen, which is probably the most important gas in the air around us. And then we also have small amounts of other things like carbon dioxide, and we'll just say ... that make up the remainder of the air around us. So when it comes to describing not just the properties of gases, but also being able to predict how gases are going to behave under different conditions. There's a theory that we use in chemistry and also in physics and in science in general to describe and predict the behavior of gases, which is called a kinetic molecular theory, which we often abbreviate this as KMT, or at least I abbreviate as KMT. And you'll see it being used in other places as well. And the idea behind this is sort of there's a lot of it entrenched in the actual name. So kinetic here meaning movement, and then molecular in this sense here would mean sort of particles. Okay, so when we talk about the kinetic molecular theory, there are four basic assumptions that we make and that we allow or that we use to describe and predict the behavior of gases. The first assumption is that a gas is composed of particles that are separated by large distances. And this actually goes back to what we mentioned in the previous section. Gases are compressible because there are lots of empty space between the gas particles themselves. And what we actually find is that if you have a container, let's say this container here, and there's gases in it, okay, the volume that the gas particles themselves would occupy, the individual particles, like these things, right, is incredibly small compared to the actual volume of the entire container that the gases or the gas would actually expand to occupy. So we say the volume occupied by the actual molecules or particles would be a better term, is negligible, meaning close to zero, compared to the actual container itself. Now, when we talk about gases being composed of particles, okay, these particles usually are either atoms or molecules, or in some cases they can be ions. But generally, when we talk about particles, we're looking at atoms or molecules. The second assumption is that your gas particles, and again, they can be molecules, they can be atoms, are constantly in a random motion. That means they possess kinetic energy, because kinetic energy is the energy of motion, and they move in straight lines, straight paths, and they collide with perfectly elastic collision. So what does that actually mean? Well, let's take a look. If I have a container, let's say I have this gas particle here, and another gas particle, and another one, and another one. So they're moving in constant random motion. So this particle here is zipping around with a great deal of speed. It is going to eventually run into this wall of the container, and it's going to bounce off. This one here is moving maybe in this general direction. You can't really predict how it's going to move. And this one here is also moving. And what it can do is it can actually collide with that particle. And when it actually collides in what's known as an elastic collision. And what that means is that the energy is transferred. In in the collisions, right? So you can think of an example of this being sort of like if you have if you're playing pool, for example, and you use the cue to hit the white ball against the other ball, so when it runs into the other ones, the energy is transferred from the cue ball, I guess, to the other balls. And it's the same idea here with your gas particles. When they run into each other, right, it causes now this second particle here to move, and it'll cause that one to run into the wall and bounce off the wall. Um, and then that repeats through the entire sample itself. Okay. Um, the other thing that we assume is that the gas molecules, the gas particles, again, would be the more generic term, do not exert any attractive or repulsive forces on one another, right? So we're assuming that there really isn't any strong forces of attraction that keep the gas molecules close to each other or the gas particles close to each other. There isn't any appreciable force of repulsion between them. And the fourth assumption is that the average kinetic energy of a gas particle in a sample is proportional to the absolute temperature. The absolute temperature is also known as the Kelvin temperature. And if you remember when we talked about kinetic energy earlier on in the second or third week of the semester, we said that the kinetic energy of a sample is simply equal to a half times mv squared. All right, and v here is the velocity or the speed, which we refer to um, as the mean square speed of a gas. So we normally would write this as kinetic energy of the gas sample is equal to 1/2 times m, and then the average or the mean square speed of the gas particles. So there are some ramifications for the different assumptions of the kinetic molecular theory. So for example, we can sort of relate what we mentioned originally or initially to those different assumptions of the kinetic molecular theory. So gases are compressible, or we can compress them because the molecules in the gas phase are separated by very large distances, right? So we talked about that a couple times already. That should make sense. There's a lot of empty space between them, which means we can compress them, we can force them closer and closer and closer together. The other result of this is that when your gases, so if I have a sample of a gas in a container filled with gas particles, eventually these gas particles will run into the walls of the container. And when they do that, what they actually um, cause is they cause now what's known as pressure, right? So pressure is simply equal to the force acting per unit area, right? So when this particular gas particle over here, for example, this one highlighted in yellow, when it runs into the wall, it exerts a force on that area, and that is what pressure is. Okay, and that's very, very important because gases will always exert pressure on the walls of the container because they're always moving around with speed, with a random motion, with a certain kinetic energy, and they will run into things, they will bump into things. What we also see is that if we decrease the volume of a gas, it will increase the frequency of the collisions, and as a result of that, the pressure will increase as the frequency of the collisions increase. So for example, if we take a look at this diagram here, okay, we have originally this thing on the left. So we have a sample of a container. There's our gas particles. They're running around, they're bouncing around. Eventually, they're going to run into the walls and exert a pressure. If we make the volume smaller, if we compress the gas, in other words, right, what happens then is the volume that the gas occupies decreases. Okay, so going from to this one now, the volume goes down, and as a result, the frequency of the collisions, so how often the collisions occur, will obviously have to increase because now there's just a smaller space that the gases are occupying. They will bump into the walls of the container more frequently, and as a result of that, the pressure increases as well. Okay, and that's going to be important because just rationalizing what's occurring in that example is part of when the reasoning behind some of the gas laws we'll see later on. The other thing that we'll notice is that if we heat a sample of a gas, what that does is it is going to increase the average kinetic energy, right? So as the temperature goes up, the kinetic energy is going to increase as well. Gas molecules then will move faster as a result of that. Faster molecules, if they're moving around with more speed, they will collide more frequently with each other and also more frequently with the walls of the container. So not only are they colliding more frequently, but they'll also collide at a greater speed. And as they do that, the pressure will increase as a result of that, right? So overall, then, if we put all these together, we can say as the temperature goes up, molecules move around more frequently. They bombard the walls of the container more frequently with a greater speed. And as a result, the pressure that they exert is going to increase as well. So what we find is that if we were to calculate the total kinetic energy of a mole of a gas, we would find that the kinetic energy would be equal to 3/2. So the kinetic energy, or 3/2, times R times T. And what R is, this is the gas constant. And the gas constant here has units of 8.314. And then you will see the gas constant with different units later on. We just use the appropriate unit for whatever problem we're doing. And then T here is your Kelvin temperature, or the thermodynamic temperature. What we saw previously also is that the kinetic energy, the average kinetic energy of one molecule of one gas molecule or one gas particle, let's use the phrase or the term particle instead, is a half times m times the root mean square, or the mean square speed of the gas particle. And you will see u, and also you'll see the v squared, right? They mean the same thing, the velocity. So if this is for one gas particle, what would be the kinetic energy for a mole? So for 1 mole, it would be that same value, but now multiplied by Avogadro's number. So Avogadro's number times a half times m times u squared. And those two now are going to be equal to each other. All right, so if we equate, in other words, the kinetic energy up here, 3/2 times RT, and then that being equal to a half, or Avogadro's number times a half mv squared. So we equate these, so we end up with 3/2 times RT is equal to NA times a half mv squared, or mu squared. What we end up with, if we rearrange our equation, right, what we will see rearrangement of this equation. Okay, so let's simplify this a little bit, this equality. So we have 3/2 times RT, and then we have, it would be NA, Avogadro's number, times the mass times velocity squared divided by 2. We can multiply both sides by 2 to get rid of the 2 in the denominator. So we end up with 3RT equals NA times m times u squared. So the product of Avogadro's number and m here is the same as the molar mass. And then that's times our mean square speed, and that's equal to 3 times RT. And if we move this over to the other side, we end up with now 3RT over the molar mass is equal to the mean square speed. And if we were to simplify this just for you, we take the square roots of both sides, and we end up now with the what's known as the root mean square speed, which is this thing here, is equal to the square root of 3RT over the molar mass of that particular gas. So what this represents uh, is the speed of a molecule or a particle that has the average kinetic energy in a gas sample. Okay, so this is the speed of a particle that has the average kinetic energy in a gas sample. A couple of things to note about this. Your molar mass here that we're using in this needs to be expressed in kilograms per mole in order for this relationship to work. All right, so we've just derived the root mean square speed, right? So that's what this is. And you'll see that being represented as the RMS subscript whenever you see that speed in your notes or elsewhere. All right, and that's what this equation down here represents. The M, the fancy looking M, this is just the molar mass, an abbreviation for the molar mass. And then for this particular equation, it's in kilograms per mole. All right, so what we find then, if we rewrite our equation, the root mean square speed is equal to the square root of 3RT over the molar mass. What this means then is that the root mean square speed is actually directly proportional to the temperature. So what this means is as temperature increases, right, the root mean square speed is also going to increase as a result of that. That's a direct relationship, directly proportional. A depiction of, we're looking here specifically now at nitrogen gas, N2, at three different temperatures, 100 Kelvin, at 300 Kelvin, and at 700 Kelvin. What we see is that as the temperature increases again, the maxima of each of these curves here moves to the right, and it also flattens out a little bit, right? So it goes from a high peak to a lower peak to an even lower peak. And the top of each of these peaks, the maximum of each curve, is the most probable speed for that sample. Now you will have gas particles in there that will have higher speed and lower speed, but the peak of each of the curves represent the most probable speed at that sample, right? So again, as you're seeing, as the temperature increases from 100 to 300 to 700, right, we're seeing that the most probable speed, right, increases from 100 to 300 to 700 Kelvin, right? That speed goes up in each of those cases. The most probable speed does. Since the curve flattens out also, right, what that suggests to us then is that as the temperature increases, you have a larger number of particles that are also moving faster. So this is comparing one particular gas, nitrogen, at three different temperatures, and you'll see that same relationship for other gases as well, when you keep the gas constant but the temperature changing. What if you had different gases? Well, we can still also predict what's going to happen based on our relationship over here. So what we'll see is that the relationship between the root mean square and the molar mass is actually an inverse one because the molar mass is in the denominator. And what that means is as we take this mathematical relationship and we interpret it, what this means is as the molar mass increases, right, the root mean square speed is going to decrease, right? That is what an inverse relationship means. And as the molar mass increases, that means the molecule or the particle is getting bigger and bigger and bigger and bigger. And if you think about this, right, at a particular temperature, and again, this is assuming the temperatures are constant in this case, the bigger the particle, the slower it is, right? And that's exactly what's going to happen if we compare chlorine, and these are all at 300 Kelvin, chlorine to nitrogen to helium, right? Helium is the lightest. It has the smaller or the lowest molar mass, and as a result of that, it's going to move a lot quicker, right? Its most probable speed is much greater. It's going to have the highest root mean square speed, whereas something like chlorine out of these three has the highest molar mass. It's the bulkiest, in other words, or the largest, and as a result, it is going to have the lowest root mean square speed. Right, its root mean square is less than 500. In the case of helium, it's over 1,000, and this is in meters per second. And that should make intuitive sense. Nitrogen kind of in the middle in the molar mass. It also has an intermediate root mean square speed as well.